The SS Great Britain, launched in 1843, is looking pretty great for her age, especially considering she's an iron-hulled vessel. I mean, we all know that things made of iron rust, so why doesn't the same thing happen to ships? Well, actually it does. The wreck of the Titanic, for example, 2 miles under the surface of the North Atlantic, is corroding away at such a rate that it will disappear entirely one day. Corrosion is a natural process, basically where an oxidation reaction leads to the deterioration of a material. It can happen to lots of different types of materials and only requires exposure to oxygen, which, as we know, makes up around 21% of the air that's all around us. Rust, on the other hand, is a specific type of corrosion that only affects iron and alloys of iron such as steel. The SS Great Britain is an iron ship, and pretty much every modern ship is made of steel, an iron alloy. So every ship does have the potential to suffer from the subset of corrosion that we know as rust. Rust occurs when iron reacts with water and oxygen to form a hydrated iron oxide. It's a kind of reddish-brown colour, and you'll notice it covering pretty much any exposed iron surface. The simplest defence is to prevent the surface from coming into contact with water or oxygen in the first place by placing a barrier in between. This is why you'll notice that everything on a ship is painted. The paint bonds with the metal underneath, creating a physical barrier to stop it coming into contact with water and oxygen. However, nothing in this world is perfect. There may be tiny gaps in the paint, and the paint itself will degrade anyway, so there will always be tiny patches of rust forming. Once the rust forms, it then flakes off and creates larger gaps in the protective coating, exposing more of the metal surface and allowing more of it to rust. Painting will protect the majority of the surface, but you'll still need constant maintenance to maintain that protection. When small patches of rust inevitably form, you need to chip away at the surrounding paintwork to expose the underlying surface and remove as much of the rust as possible. After that, simply apply something like phosphoric acid to chemically break down any remaining rust and expose the underlying iron or steel. Sometimes the rust remover will contain tannic acid, which reacts with rust to form a black protective coating over any remaining patches. It's not so much for the coating itself, but more for the black colour, which helps highlight any remaining rust that needs to be removed. Once the surface is all cleaned up, it's just a case of reapplying some paint with some underlying primer to encourage bonding and a top coat of something hard wearing and weather resistant. But painting isn't the only weapon in our arsenal for fighting rust. Back in the 1800s, a new type of corrosion protection was developed and fitted to HMS Samarang. She was a wooden ship with a copper-sheathed hull where the copper was applied to protect the hull from woodworm and marine growth. They wanted to prevent the copper from corroding, so they fitted some sacrificial anodes in what became the first known application of cathodic protection. The idea is that when two metals are connected together, the one with the lower electrode potential will act as an anode and the other will act as a cathode. Essentially, electrons can flow freely from the anode to the cathode, making the anode more positively charged and the cathode, the ship's hull, more negatively charged. The end result is that the anode will corrode as a sacrifice, lessening the corrosion of the cathode. The sacrificial anode just needs to have a lower electrode potential than the cathode. In the case of HMS Samarang, an iron anode was used to protect the copper sheathing. The irony was that it was so effective at preventing corrosion that the ship then suffered from an increase in hull growth, which had previously been prevented by the corrosion process itself. In the end, they abandoned cathodic protection because preventing marine growth was far more beneficial than preventing the corrosion of the copper. Of course, on modern ships we have iron or steel hulls which we want to protect because there's no such secondary benefit in letting them corrode. Again, you just need an anode with a lower electrode potential than the iron in the hull, so zinc or magnesium are ideal. Notice how this is the exact same concept that we use with galvanised nails. An iron nail can be galvanised with a coating of zinc. The sacrificial coating will tend to corrode first, preserving the underlying strength of the nail. Anyway, to fit an anode to a ship, if the hull is made of steel, then you can literally bolt it straight to the side. You'll want to make it streamlined to cut down on drag, of course, but for the cathodic protection, you just need a conductive connection between the hull and the anode. For fiberglass or wooden hulls, however, you still bolt the anode to the side of the vessel, but you then need to create an electrical connection to anything that you want protected, such as the main engine. Over time, the anode will corrode away. Remember, it isn't made of iron, so it can't rust, but it can corrode. The sacrifice is worth it though, because it's much cheaper to periodically replace a sacrificial anode when your vessel's in dry dock than it is to replace for example parts of the main engine, because they've started to corrode instead. You see, it's this ongoing maintenance, like replacing the sacrificial anodes and continuously chipping and repainting rusting sections of the hull, that stop metal ships from rusting away. Left unchecked, like 2 miles under the surface of the North Atlantic, natural processes will kick in and even the grandest of ocean liners will eventually rust or corrode away entirely. Finally, I would just like to extend a massive thank you to this channel's Plus supporters on Patreon. You voted for this topic and it turned out to be a fascinating one to make, so thank you all so much.